All right, let's jump right in. Today's explainer pushes the universe to its absolute breaking point. We are exploring the radical, unified dynamics framework. This is a completely different way of looking at the foundational architecture of reality, drawn directly from our source materials.
So think about this for a second. What if space and time aren't this smooth, continuous fabric like we've always been taught? What if, instead, reality is a pixelated grid with a strict data limit? Imagine reality itself is fundamentally discrete, has a hard maximum capacity, and under extreme stress, it literally just maxes out. To get there, we've got a quick roadmap today. We're going to hit the illusion of space-time, the universe's hard capacity limit, extreme gravity's breaking point, hunting for gravitational wave anomalies, and finally the Planck scale UV cutoff. Let's get to it.
Part 1. The illusion of space-time.
Standard physics really leans heavily on the idea of a smooth, continuous universe. But we all know that when you push that math to its extreme limits, it completely breaks down into impossible singularities. Unified dynamics, it abandons that continuous vacuum entirely. Instead, it replaces it with a dynamically evolving, discrete tetrahedral graph known as the K4 network. At this foundational layer, there is actually no physical dimension, no length, no time, no mass. There is only combinatorial adjacency.
Moving on to part 2, the universe's capacity limit. Now, if reality is a discrete network, it logically must have a maximum capacity, right? There has to be a boundary where the system experiences what the sources call lattice shear. To understand this limit, we have to look at the processing burden. This is just the quantitative accumulation of unresolved state updates at a specific discrete node. Think of it like a cosmic traffic jam, or even like digital lag. If a single node gathers too many unresolved updates, the local coherence of the graph threatens to drop below its bare solvency threshold. And that brings us to a very specific, absolutely crucial number: 7/768. The Unified Dynamics framework mathematically derives this exact fraction as the absolute point density resolution limit. It's the physical bedrock capacity of a single vertex in the premetric network.
So what happens when a vertex actually hits that 7/768 threshold? Well, to prevent a cascading structural collapse, the network physically has to route this burden, this data debt essentially, to its neighbors. And what's wild here is that this fundamental algorithmic necessity to move structural debt is exactly what manifests macroscopically to us as momentum, forces, and physical transport. Motion is literally just the algorithm preventing local geometric collapse.
Which brings us to part 3, extreme gravity's breaking point.
Let's apply this hard physical boundary to the ultimate cosmic stress test, the center of a black hole. In a discrete network like this, infinite singularities simply vanish. When an object falls straight down a gravity well, standard math says it crushes to an infinite density. But here, it hits what's called the saturation floor, or the RD interface. Because a single vertex has that fixed carrying capacity we just talked about, the geometry physically cannot accept more density. It acts as a hard mathematical stop. Any excess mass energy is physically shunted right into adjacent topological states.
All right, part 4. Hunting gravitational wave anomalies.
If the continuous space-time manifold really does break down at extreme mass densities, we should absolutely be able to detect it. Unified Dynamics predicts that an emergent 4-channel accommodation architecture takes over during these extreme events. These specific discrete channels, theta, A, C, and B, act as physical shock absorbers to handle the extreme congestion. The continuous illusion shatters into these channels, generating testable non-classical deviations. We can basically think of them as glitches in the matrix or very specific gravitational wave anomalies.
And what's super exciting is that these abstract anomalies map perfectly to real-world observatories that are gathering data right now. For the A channel, terrestrial interferometers like LIGO can look for merger entry distortion. This is an anomalous structural compactness during a late inspiral phase. For the C channel, the upcoming LISA Space Observatory will be targeting split or enriched ringdowns that contain non-classical harmonics. And for the B channel, the proposed Cosmic Explorer will be hunting for persistent organized remnants which show up as very specific memory tails.
Now, the sources emphasize this heavily. These aren't just guesses. They are strict zero-parameter predictions, making this framework highly falsifiable. If LIGO events match classical numerical relativity perfectly with zero anomalous compactness, the discrete channel saturation limit is falsified, dead in the water. If LISA ringdowns lack non-classical harmonics, falsified. If Cosmic Explorer sees strain return to absolute zero without a persistent offset, the entire network routing topology is completely falsified.
Finally, Part 5, the Planck scale UV cutoff. So how does this discrete logic handle the highest energies possible? Standard quantum field theories usually require completely arbitrary mathematical tricks, renormalization, just to handle infinite ultraviolet energies. But unified dynamics posits a strict UV cutoff limit natively anchored right to the Planck mass. This is the ultimate spatial diffusion boundary where that 7/768 vertex capacity limit is definitively breached at the Planck scale. The physical smearing of the point particle is mathematically locked to the absolute limits of this combinatorial substrate.
This framework also natively addresses the massive scale differences in our universe, what physicists call the hierarchy problem. Through an elegant geometric process called Banach screening, it securely bridges the staggering 10 to the 46 magnitude gap between the microscopic Planck scale and the macroscopic standard model. As discrete topological information projects into continuous limits, it is geometrically screened. This massive scale suppression is derived exactly from the intrinsic geometry. Nothing is added by hand.
The universal structure theorem dictates a very strict sequence here. Step 1. You anchor the absolute physical scale with exactly one empirical measurement, the Planck mass. Step 2. Apply the parameter-free geometric scaling flow natively derived from the network's intrinsic deficit ratio. Step 3. Natively derive the continuous structural ratios of the standard model. It strictly forbids phenomenological curve fitting just to make the math match our observations.
Because it operates without those free parameters, the authors boldly lay down this ultimate null test for high-energy physics. If colliders ever discover a fundamental structureless point particle exhibiting continuous structural integrity above the Planck energy, the framework fails. Find a truly continuous particle exceeding this energy, and the entire discrete, capacity-limited architecture is immediately invalidated.
So as we wrap up this explainer, I want to leave you with something to chew on next time you're looking up at the night sky. Is the universe really just an infinitely detailed, smooth illusion? Or is it actually a hard, calculated grid actively routing data just to prevent its own structural collapse? Thank you so much for exploring the absolute edges of extreme gravity with me today. Until next time, keep questioning the framework of our reality.